You all know what it means for a solution to be dilute. What that means, of course, is that there is a lower or smaller amount of solute dissolved into the solution. So a dilution is where you are basically making a solution more dilute. You are either adding, well, typically you're going to be adding more solvent to the solution to make the proportion of solute to solvent smaller. So the way we're going to calculate this for a dilution calculation is quite simple. Basically, it's M1V1 equals M2V2. Now, what that means in regular English is the molarity of your first concentration multiplied by the volume of your first concentration equals the molarity and the volume of your final concentration or your final conditions. So again, just like you learned before in previous units, the ones on the left are for your initial conditions. The twos on the right are for your final conditions. Again, they are both molarity times volume. Let me just remind you really quickly, mathematically speaking, it doesn't matter if you put molarity before volume or volume before molarity. All we need to worry about when we do this calculation is that we have both the molarity and volume for the initial conditions on the left and for the final conditions on the right. Again, other than that, the order of those two don't make any difference whatsoever, so don't stress about that. All right, so let's try to see our first dilution problem. Number 5, it says, what concentration results when water is added to 500 milliliters of 12 molar hydrochloric acid to prepare a 2 liters of solution? So what concentration results? So that means we're looking for M2. I'm just going to put M. When water is added to, here's our original volume, 500 milliliters of a 12 molar hydrochloric acid solution to prepare a 2-liter solution. Okay, now the only problem here is our volumes do not match. We have milliliters and we have liters. We really need to fix that. The easiest way to do that, of course, is to move the decimal 3 spots to the left, or basically divide by 1,000. So I'm going to move this into 0.5 and take out this milliliter. So now, again, we have the same volumes. The volumes must match. It doesn't matter if they're both milliliters or if they're both liters. Mathematically, they just need to be the same. So what I'm going to do now, of course, mathematically speaking, is I'm going to divide this side by 2 liters, cancels that out. Do the same thing on this side to make sure that they, to get our M all by itself, this will all cancel, leaving us with just our molarity. So 12 times 0.500 divided by 2.00, that gives me a molarity of 3 molar. There's our answer. That's the molarity that it would be diluted to. Notice my dilution of my final concentration is 4 times less than my original 12 molar, because again, it's dilution. You can't dilute and become more concentrated. That's not really possible. That's not really called a dilution. That's when you're concentrating something. That's the opposite side of the equation, I guess. I'm not sure what to say there. Number 6, it says a 3.34 molar sodium chloride solution is diluted by adding 35 milliliters of distilled water to 50 milliliters water of the solution. And of course, they want us to calculate the molarity. So this one's a little bit odd in that the wording is not very clear. Number 5 was not that difficult to figure out what our original molarity and volume were and our final molarity and volume. Number 6, they kind of make it a little complicated. So what we have here is we have our original 3.34 molar solution is diluted by adding 35 milliliters. That is not my original volume. We're going to add that to 50 milliliters. So if you think about it, our original volume is actually 50 milliliters. Then we're going to add 35 milliliters to it. So my final volume is not 35 or 50. It's actually going to be 85 milliliters because we added 35 milliliters to our original 50 milliliters. What that's going to give me, of course, is my final molarity. So again, as you guys already know, I'm going to move this 85 molar down here. That will cancel that out. So we have 3.34 times 50 divided by 85. And my final molarity comes out to be 1.965 molar. Okay, so number 6 again is not very difficult, other than they kind of make the volumes look a little bit tricky. They say we're going to add this much to this. Well, what the 2 is the original, and what you added is what you have to literally add. Number 7 is a little tricky, okay? They're going to throw a curveball at us for number 7. So they say how many milliliters of 12 molar hydrochloric acid and how many milliliters of water, so that's interesting, are needed to be mixed together to make 750 milliliters of a 1.11 molar hydrochloric acid solution. So what I'm going to start off with is my M1V1 equals M2V2. So my original volume, how many milliliters of this, of hydrochloric acid, of 12 molar hydrochloric acid, is needed to be mixed to make 750 milliliters of a 1.11 molar hydrochloric acid solution. So again, you guys know I'm going to take my 12 molar, divide it over here. That cancels that out. So my volume of just the hydrochloric acid, or hydrogen chloride actually, to be technical, is going to be my volume of the hydrogen chloride solid. It's not an acid, but it's solid. You guys will learn that soon. That's why I'm not calling it hydrochloric acid. Is 69.375 milliliters. Why milliliters? Because that's what my other volume is, and it's going to match. Now, this is the different part. We know that the final volume is going to be 750 milliliters. So if my final solution, aqueous solution, is 750 milliliters, and I've already calculated that I'm going to add 69.375 milliliters of hydrogen chloride, then I need to find the difference to figure out how much water I'm going to have to add to that hydrogen chloride to make 750 milliliters of a 1.11 molar hydrogen chloride, hydrochloric acid solution. 750 minus 69.375 gives me 680.625 milliliters of H2O. That's the amount of water we would have to add. This is the amount of of solid hydrogen chloride we'd have to add. When we mix those together, we would have 750 milliliters of a 1.11 molar solution of hydrochloric acid.